Precal. We're doing double angle identities. Got to pay attention to it. It's not terribly difficult, but there's a couple of ins and outs you got to watch out for. So the first thing I'm going to do is to derive or develop the formulas that you're going to need to use. Make sure you have them handy when you go to do your work. So sine of 2a, I'm going to first use the sum identity, rewrite 2a as a plus a. Rewrite 2a as a plus a. Then we're going to use the sine song, sine, cosine, cosine, sine. I say again, sine, cosine, cosine, sine. Sine, cosine, cosine, sine. Sine keeps the sign the same. So we got sine of a times cosine of a plus cosine of a times sine of a. Well, cosine of a times sine of a is the same thing as sine of a times cosine of a, just the commutative property is all that is. So really you're adding two of the same thing. So there's one identity for sine of 2a, and it turns out to be 2 times sine a times cosine a. Very simple. Now to do the double angle for cosine, we're going to start the same way. Cosine of 2a is equal to cosine of a plus a. And cosine goes cosine, cosine, sine, sine. Cosine, cosine, sine, sine. Cosine changes the sign though, so since we have addition here, when we come out, it's subtraction. So we have cosine a minus sine a, sine a. Well, cosine times cosine is cosine squared, and sine times sine is sine squared. So cosine of 2a turns out to equal cosine squared a minus sine squared a. This is one of 3 double angle identities for cosine. Notice sine only has one. Cosine's going to have 3 versions. This is the primary one. So to get the other 2, we need to just simply remember the Pythagorean identity that sine squared a plus cosine squared a is equal to 1. So that gives us something else we know. If we subtract cosine squared a both sides here, we get sine squared a is equal to 1 minus cosine squared a. And if we had subtracted sine squared a both sides here, we would get cosine squared a is equal to 1 minus sine squared a. Using one of these at a time, we can come back to the first version and substitute. So by substitution, cosine of 2a, here it is, would equal, leaving cosine squared a as the first part, minus, and then wrapping up in parentheses, what sine squared a equals. And sine squared a is equal to 1 minus cosine squared a. So we substitute. Distribute the minus sign, and when you do, minus minus becomes plus. So we have cosine squared a, what's going to be plus cosine squared a, which will be 2 of them, and then minus 1. So here's the second double angle for cosine. Cosine of 2a, yes, it equals cosine squared a minus sine squared a. It also equals 2 cosine squared a minus 1. And again by substitution. We go back, we have cosine 2a equals cosine squared a minus sine squared a. But this time we replace cosine squared a with 1 minus sine squared a. So we come here, replace it with 1 minus sine squared a. Then we still have minus sine squared a here. And minus sine squared a makes that minus 2 sine squared a. So the third and final version for cosine 2a is 1 minus 2 sine squared a. Now for tangent, stay with me. Tangent of 2a is tangent of a plus a. And again, using the tangent identity for a sum, it goes tangent angle plus tangent angle over 1 minus tangent angle times tangent angle. The angle is the same angle a, so we have tangent a plus tangent a as the numerator, 1 minus tangent a times tangent a as the denominator. Tangent a plus tangent a is 2 tangent a, and then 1 minus tangent a times tangent a gives me 1 minus tangent squared a. Now we'll begin by doing some examples so you can see how these identities work. So the first one, if you look at the top here, it says page 394. And to do this problem, well, it looks like that might have got cut off, but the top, which you might not have seen, simply said examples, page 394. And this is number 4 from page 394, where they drew a right triangle. They put an angle here. They've got the Greek letter theta. The right angle indicator is here. The side opposite theta is 1, and the side adjacent to theta is 4. We're going to have to find the hypotenuse to do this problem. The hypotenuse is found by using the Pythagorean Theorem. So we go leg squared plus leg squared is equal to the hypotenuse squared, and I'm going to call the hypotenuse C. That would be this side. We're going to call it C. 4 squared is 16, 1 squared is 1. 16 plus 1 is 17, so if c squared is 17, we would do square root to find that c is equal to square root of 17. That's just Pythagorean Theorem. So the first part of number 4 asked me to find sine of 2 theta. Then it's going to ask me later to find cosine of 2 theta. And lastly, tangent of 2 theta. So I would recommend that you write these identities down as often as you need to use them, and we do in this problem. So sine of 2 theta is equal to 2 sine theta times cosine theta, which is equal to 2 times. Well, to get sine theta, we come back to the given triangle, and we recall that sine of theta in a right triangle is opposite over hypotenuse. I say again, sine of theta is opposite over hypotenuse. We found the hypotenuse is square root of 17. So the sine of theta is side opposite, which is 1, over hypotenuse, which is square root of 17. So we made that substitution right here. Sine theta is 1 over square root of 17. Multiply that by cosine theta. Back to the right triangle. Cosine is adjacent over hypotenuse. The adjacent side is 4. Again, the hypotenuse is square root of 17. So the cosine of theta is 4 over square root of 17. To finish this problem, 2 times 1 times 4 gives the numerator 8. And the bottom, square root of 17 times square root of 17. We're squaring a square root. They undo each other. That leaves me 17. So sine of 2 theta is simply 8/17. Moving to problem 6. I think I might have misspoke on 4. I only did sine of 2 theta, so that might be all it asked me for. Number 6, secant of 2 theta. So secant is the reciprocal of cosine, so I rewrote it 1 over cosine of 2 theta. I'm going to use the identity that cosine 2 theta is equal to cosine square theta minus sine square theta, because I've already got all 3 sides of this triangle found. So I come here and I make my substitution. 1 over cosine squared theta. Well, cosine theta, if you look back here, cosine theta was 4 over square root of 17, which we got from our triangle. So on the bottom, we're going to square that 4 over square root of 17. Minus, and we're going to square our sine value. Sine was plugged in here, and we got that also from the triangle. So we have minus sine squared theta is minus 1 over square root of 17 squared. Still 1 over, square 4, you get 16. You square the square root of 17, you get 17. Minus sine. You square 1, that's 1. You square the square root of 17, that's 17. 1 stays the top. 16/17 minus 1/17 is 15/17. 1 over fraction means reciprocal of fractions. So the final answer to number 6 is 17/15. Number 14, and ones like it. They want me to solve these trig equations, and it's going to involve using the double angle identity for one of the ones we've learned about. So I'm solving for 14. Cosine of 2x plus sine of x equals 0, where x is an angle on the interval 0 to 2 pi. The angle can equal 0, but not 2 pi. The first thing I did was I noticed this was sine x, and this was cosine 2x, and I want to solve this by getting one trig function. So what I did was I went back to the original formulas, and if you'll either rewind and replay this video or look at your notes or textbook, one of the identities for cosine of 2x is 1 minus 2 sine squared x. So I made that substitution right there. Cosine of 2x is 1 minus 2 sine squared x. Then plus sine x equals 0. Now what I'm going to do is multiply everything here by -1, everything by -1, and reorder it. So negative times negative is going to become positive, so there's 2 sine squared x, minus sine x, because again I'm multiplying by a negative, and then minus 1 equals 0. I factor it. I have 2 times sine x plus 1 times sine x minus 1 equals 0. And that's true because 2 sine times sine is 2 sine squared of x. 2 sine x times -1 is negative 2 sine x. 1 times sine x is 1 sine x. And when I add negative 2 sine x to positive 1 sine x, that gives me a negative sine x. 1 times -1 is -1. I'm coming this way. I'm setting this first factor equal to 0. I subtract 1, and I get 2 sine x is equal to -1. Then divide both sides of this by 2, and I get sine x is -1/2. I pay attention to the fact I'm on the interval 0 to 2 pi. Sine is negative for angles x in the third and fourth quadrant. So the third quadrant angle where the y-coordinate is -1/2 is the angle 7 pi over 6. The fourth quadrant angle where the y-coordinate is -1/2 is 11 pi over 6. I take the other factor, sine x minus 1, set it equal to 0. That gives me sine x is 1. And there's only one place in the unit circle where the y-coordinate is 1. That's where the angle is pi over 2. So that's that solution. I think you can see it all there. Okay, we got a little bit more to do. Now we have page 394, number 26. They give me cotangent of u is equal to -4. They tell me the angle u is between 3 pi over 2 and 2 pi. If you think about that or pull out your unit circle and look, if your angle is between 3 pi over 2 and 2 pi, you're doing your work in the fourth quadrant. That's going to matter to us. For 26, they give me what cotangent of u is equal to, and they want me to find the values of sine of 2u, cosine of 2u, and tangent of 2u. The first thing I do is I rewrote cotangent as cosine over sine, because cotangent is x-coordinate over y-coordinate, which is the same as cosine angle u divided by sine angle u. And I rewrote -4 as 4 over -1. Notice I put the negative in front of the 1. That's because, since I noted I'm in the fourth quadrant, in the fourth quadrant, x-coordinates are positive, y-coordinates are negative, so I allowed that negative to go to the sine value and not the cosine value. The next thing you'll notice is the 4 and the -1 both now become fractions. 4 over square root of 17, -1 over square root of 17. Because there is no angle on the unit circle where cosine is ever larger than 1. So what I had to do was I had to convert these values into values that would belong to the unit circle. And I did that by using the Pythagorean Theorem. I treated this as an x-coordinate, and this is a y-coordinate, but I know that the circle would not be a unit circle, so I had to figure out what the radius of that circle would be. So I went 4 squared plus -1 squared. Well, 4 squared is 16, -1 squared is 1, and 16 plus 1 is 17. So the hypotenuse, therefore, would not be 17, it would be the square root of 17. Don't forget, angle u is in quadrant 4. So sine of 2u is equal to 2 times sine u times cosine u. That's our double angle identity for sine. Sine is right here, -1 over square root of 17. Cosine of u is up here, 4 over square root of 17. And I've got them written out already, so I can now make my substitution. And there it is. There's the 2. Sine of u, we said, is -1 over square root of 17. Cosine of u, we said, is 4 over square root of 17. 2 times negative 1 times 4 is negative 8. And square root of 17 times square root of 17 is just 17. So sine of 2u is negative 8/17. For cosine of 2u, double angle for cosine, I wrote that it equals cosine squared u minus sine squared u. That's our first and primary double angle identity for cosine. I go back to this ratio and I make the substitutions because I've already got everything written down. Cosine is 4 over square root of 17. There it is. Sine is negative 1 over square root of 17. There it is with a square and a parentheses wrapped around, and that's the minus sign of the formula here. If you square 4, you get 16. If you square square root of 17, that's 17. Minus sign. If you square negative, you get a positive. Square 1, you get 1. Square square root of 17, you get 17. 16/17 minus 1/17 is 15/17, and that's cosine of 2u. The last one, tangent 2u. I did it the long, hard way. And I'm going to show you the shortcut, easy way once I finish this long, hard way. Having already done sine and cosine, there's a quick way to get what tangent is, but we'll go ahead and use the identity because we need to know our identities for all the different work we do. Tangent of 2u we found in the first page of work we did on this video is equal to 2 tangent u over 1 minus tangent squared u. Remember, tangent is sine over cosine, but tangent's also the reciprocal of cotangent. So that was nice. They gave me cotangents 4 over negative 1, so tangent would simply be negative 1/4. You just flip it. Same thing down here, 1 minus tangent squared. Since tangent was negative 1/4 up here, it's negative 1/4 down here, but down here we're squaring. 2 times negative 1/4 is negative 1/2 because 2 goes into 4 2 times. 1 minus, square negative 1/4, you get 1/16. So the negative 1/2 remains the numerator. Negative 1/2 remains the numerator. 1 minus 1/16 is 15/16. That's what this is, 15/16. When you divide fractions, you take the numerator fraction and multiply by the reciprocal of the denominator. Multiply by the reciprocal of 15/16, that's 16/15. 2 goes into 16 8 times, so the final value of tangent of 2u is negative 8/15. And look, what I could have done, I could have taken the sine value, divided by the cosine value, the 17s would have canceled, and I'd have quickly got my negative 8/15. The assignment, which will be due on Monday, April 27th, and I think this is also pretty much posted accurately on Gradebook Wizard's website, page 394, numbers 1 through 8 all, 9 through 17 odds, also 23, 24, and 25. Rewatch this as many times as you need to. Check out your textbook or go to the internet and look up other videos to help yourself out and show up in Zoom. See you tomorrow.